And hello everyone, I'm Serdar Özsoy, and I'm going to present our work on self-supervised learning with an information maximization criterion. This is a joint work with Shadi Hamdan, Shadi Hamdan, Serdar Özsoy and Alper Erdoğan. It's accepted to NeurIPS 2022, and we presented it in there at the beginning of this month. Now I'm starting with the first part, and Shadi will continue in the second part of the presentation. Today in our world, an enormous amount of data is produced by different sources. In supervised learning, we can only use small fragment of this produced data because there is a need to label data set to use it. However, this task is usually expensive in terms of time, effort, and so cost. Labeling creates a bottleneck for supervised learning. We can come up with a question: can we take advantage of using all data produced and learn useful representations without labeled data? And this question led us to unsupervised learning. And starting from 2016, one of the pioneers of deep learning, Yann LeCun, is introduced a cake analogy, which provocatively emphasized the unsupervised learning. And this famous analogy is updated during the years, and this unsupervised learning part is changed to the self-supervised learning as self-supervised learning in order to be more specific. And based on information content per sample, this self-supervised learning proposed as the main part of this learning cake. So during that period of time, self-supervised learning in NLP showed great impact, and such as GPT, BERT, and so on. And this fact is triggered an increase in the number of self-supervised learning research in computer vision. And for self-supervised in computer vision, typically two different augmented versions of the same input are fed into the encoder and projector networks to obtain output representations. Objective is minimizing distance between Z1 and Z2, and in other words, bringing these representations close to each other for the same input. However, this setting should avoid a major problem called collapse. First type of collapse is the total collapse, and all representations, all output representations converge to a single point during training. For different inputs, we get the same constant value as the output. And second type of collapse is dimensional collapse, for which output representations lie in a strict subspace of the whole space and not effectively use the whole output representation space. And so before diving into the details, we can summarize the main idea of our work as correlative information maximization among alternative latent representations of the same input naturally prevents dimensional collapse in self-supervised learning. In that way, you can also prevent the total collapse. And the remaining part of the presentation, we will go shortly over the existing self-supervised learning methods in computer vision. Then we will introduce the CorInfoMax objective, and we will briefly explain how we come up to CorInfoMax objective from the LDMI, and finally we will share our experimental results. Let's look at how existing methods deal with this collapse problem. And the methods on the left-hand side can be named as contrastive loss-based methods, and uses info NSE is a contrastive loss and prevents the collapse in Sinclair and Moko. And contrastive loss is required to use larger number of negative samples, and that makes use larger batch sizes, required to use larger batch sizes. And MoCo use a Q as a dynamic dictionary of these negative representations to eliminate using larger batch sizes. And on the right-hand side, there is BUOL and CM. These methods can be called as distillation-based methods. And asymmetry in this asymmetry is created in these architectures. These methods are by architecture, and they do not use negative samples in loss calculation. And collapse is avoided in these methods by using stop gradient operator for one branch. And we continue with different types of methods in this page. The methods on the left-hand side can be named as cluster-based methods. And a deep cluster method iteratively produce latent representations and then use k-means clustering on these representations to create pseudo-labels, and then learn to classify these pseudo-labels by using these representations. Collapse is preventing by assigning new centroids for the empty clusters, or sampling inputs by using on a uniform distribution on the pseudo labels, but clusters are refined in each epoch. That's not scalable for large data sets. So SWAW in the below is proposed with online clustering method as an improvement. So the methods on the right-hand side can be named regularization-based methods and use decorrelation of output representations to prevent collapse. Above Barlow-Thibbins, main objective of Barlow-Thibbins is a convergence of normalized cross correlation metrics of output representations to the identity metrics. Below, WICREC is based on the similar idea but with different cost terms. And actually, in WICREC, standard deviation of representations of standard deviations along batch dimension of the representations are equal to 1, making triangle equal to 1, and of diagonal entries of covariance matrix of representations, trying to making equal to 0. And so also MSC makes pairs to close each other. And in information maximization perspective, also there are two main ideas. The first one is the InfoMax, is preservation of maximum information between input and output representation. And another direction is proposed by Baker and Hinton, and which maximization information between outputs of different parts of the same input. And so our method is mostly shows similarities between the second one. But in the literature, there is also self-supervised learning method. There are also self-supervised learning methods uses InfoMax structure. So in deep InfoMax method, deep InfoMax method and MDIM method, augmented multiscale deep InfoMax, they are using different levels of maximize the information between different levels of the information. And as differently in Barlow twins, they are using information bottleneck objective function. They tries to maximize mutual information between input and output representation while reducing the mutual information between output representation and augmented input representation. So we are differing from also Barlow twins from that side. And we have seen existing methods in self-supervised learning and examine about the information maximization perspective also. With CorInfoMax, we propose a novel self-supervised learning method based on information theoretic foundations, which naturally avoids the dimensional collapse problem. And CorInfoMax relies only on second-order statistics and does not require negative samples and does not force embeddings to be uncorrelated. And this objective function is a force obtained through a first-order approximation of the log-determinant mutual information, which we'll go through in the following slides. Moreover, it restricts the linear dependence to the identity map. The proposed CorInfoMax objection and two main components. The first one is the Big Bang factor that makes feature representations expand the feature representations along the feature space. So the second one is the attraction factor, which makes getting positive samples closer to each other. And arrows are black arrows show the Big Bang factor gradient forces. So white arrow also shows the attraction factor gradient force. And starting from LDMI to CorInfoMax journey start with log-determinant entropy. It's introduced by Liu and also Erdogan. And for a random vector X, log-determinant entropy is a second-order statistics-based randomness measure, and which is a modified form of Shannon entropy for Gaussian vectors. And here Rx is the covariance of the vector X, and epsilon is the small perturbation parameter on covariance. And corresponding log-determinant mutual information, LDMI between two random vectors, can be written as difference of two log-det expression. The first log-det expression is obtained from the Rx, is the covariance matrix of X. And the second involves as covariance matrix of error, Re, which is essentially the error covariance of the best linear MMC estimate of X given Y. So, and the following lemma asserts that this LDMI is an information measure reflecting the correlation or linear dependence between two vectors. As the self-supervised learning objective, we propose maximize LDMI between two output representations, Z1 and Z2. With this purpose, we also calculate Z2 and Z1 and take the average. However, this in this format is computationally expensive, and also we want to make an simplification for the self-supervised learning. First, we approximate with the first-order Taylor series, and by using this Taylor series expansion, we obtain the trace of the error covariance for estimating Z1. Z1, but linearly from Z2 for based on the mean square error criterion. And we can write it as a result of the optimization as a blue part, and also doing same for the latest term, and we obtain this. But for the sake of self-supervised learning, we don't want to make arbitrary linear dependence. We want to make identity mapping between representations. So we enforce the make A1 and A2 is to the identity mapping, and B1 and B2 to the 0. So we obtain our objective function by scaling with the expression by 4. So this is actually deterministic version of it, but for the using sample-based version, we make this change for the sample-based estimate version for the ELK batch, and we have used in our experimentation this objective. And let me remind you what is doing with this objective function. With the Big Bang factor, we expand the whole future representations to the whole feature space. By doing this is avoiding the collapse, but to learn meaningful representations, we are also getting closer positive samples by the attraction factor that provides very powerful, very learn good representations for our architecture. And Shadi will continue with our experimental results.
Okay, so is my audio okay? Just to double check. Okay. So then we go on to our experimental results. And the way we would like to evaluate what we need to do is to evaluate basically whether the representations that are learned using our CorInfoMax algorithm are useful for multiple downstream tasks. And the most straightforward way is to basically evaluate it for image classification. And the setup in which we do that is basically the encoder in this case is frozen. So we do not, it's not updated during this process. And then we simply train a single projector layer on top of it, a single layer, which basically projects from the output dimension of the encoder to the number of classes. And during this scheme, we use 100% of the training data. So we basically use the entire training set and evaluate it personally, validation set. And in this slide, we can see the top one accuracies of multiple models compared to ours on this linear evaluation. We worked with 5 different data sets, CFAR10 and CFAR100, and 3 variants of ImageNet, namely Tiny ImageNet, ImageNet 100, and ImageNet 1000. We also tried 2 different backbones, ResNet 18 and ResNet 50. The entries marked with dash are those that we could not find any publicly available metrics for. Unfortunately, we could not reproduce all methods due to time constraints and budget constraints. So the entries marked with bold are those that are the best or within statistical margin of the state of the art. So as you can see, CorInfoMax achieves either state of the art or very close to state of the art in all data sets that we have evaluated on. And basically in ImageNet, it's within 0.22% of the state of the art, which is beyond. So another thing that we wanted to evaluate also is whether the encoder can, the learned representations can easily adapt to new tasks. given a small data set. So to do that, we follow a semi-supervised approach, which is basically after pre-training using CorInfoMax on a large unlabeled data set, we then fine-tune. In this case, we fine-tune both the encoder as well as the linear classifier on a small subset of a data set. So in this case, we only use 10% of the labels or even 1% of the labels. And basically, this will tell us whether our representations are easily adaptable to new tasks or not, which is useful for many scenarios where you don't have a lot of labeled data for a given task. And in this slide, we can see the top one accuracies in this scheme for ImageNet 1000 after 100 epochs. And this we evaluated both using 1% of the samples as well as 10% of the samples. And in both scenarios, we were able to achieve better performance than VicReg, which is the other paper that reported similar experiments. And especially in the case of 10% of samples, we achieve better results. So the previous experiments were classification experiments. And what these experiments show us is whether the model learned global features. So like whether there's a cat in an image or not, or like whether there's a certain object in the image or not, which is what classification evaluates. What we also wanted to look at is whether the encoder learns like localized features. And to do that, we also evaluated on other tasks, such as like object detection and instance segmentation, which require the model to basically learn fine-grained features on a pixel level. And to do that, the setting is, so if you look at the encoder here, it's cropped because, and this is because we take the first 4 blocks of ResNet. This is also called like a C4 backbone based on ResNet. And we basically use this in a masked RCNN model. Again, the encoder is frozen, so there are no gradient updates that flow to the ResNet backbone. And then we basically add like the region proposal network and the classifier parts of masked RCNN, and we use the entire data set in this scenario. And in we evaluated this on both COCO for object detection as well as instance segmentation. And we report AP50, AP, and AP75. And as you can see, we achieve pretty similar performance to MOCO V2, which is, again, the other approach which we found publicly available metrics for. And what this tells us is that CorInfoMax does not only drive the model to learn like these global features, which are useful for downstream classification, but we also learn localized features which allow the model to adapt to different tasks that require fine-grained representations. Another concern that was possibly raised during our approach is this log determinant operation in the loss function and how that might impact the complexity of the approach. So what we did is we also ran different experiments on different projector dimensions and how much that increasing the dimension of the last projector dimension, how much does it affect the computation complexity. And basically we looked at sizes from 64 up to 1020 or 1024, and this is higher than what we got the best performance with to begin with. And what we see is that although there is an increase in the time, in the computation complexity of the loss function, it remains like within a reasonable margin, especially for like when we go as high as 512, which is what our best hyperparameters were around. Another experiment that we did is we also looked at the proportion of the time that is spent in the log determinant calculation. We did this on ImageNet 100, ImageNet 1000, the full ImageNet, and ResNet 50. And on a V100, basically, what you see in the table is for different batch sizes and different projective dimensions, how much of the, what percentage of the time is spent for this log determinant calculation. And what we see is that basically, even in the case of like 1024 projective dimension, a large portion of the time is still being dominated by the backbone ResNet 50 calculation and other parts of the model. So it only contributes around like around 5%, even in the worst case. And as the batch size increases, this also decreases because this is a factor of the projective dimension and not the batch size. Basically, what we see is that it basically has negligible impact on the overall computational cost, especially considering the improvements in performance. So another interesting measure, another interesting experiment that we did is we also looked at the evolution of the LDMI measure, the log determinant mutual information, during training. And we basically looked at the graph of how the LDMI measure evolves during training compared to how the test accuracy evolves during training. We did this for both CFAR 10 and CFAR 100. So basically what you see in the table is on the right, we have the LDMI measure in orange, and on the left, we have the test accuracy in blue. And as you can see, they both rise, there's a correlation between like the increased log determinant mutual information and the test accuracy. These experiments were all done using our CorInfoMax loss function. So basically, this tells us that also like our CorInfoMax approach optimizes for both the increases the LDMI, and as a result, we also get higher test accuracy. And yeah. Another interesting experiment that we did is we also wanted to see whether we are achieving what we wanted to do, which is basically we wanted the model to use the entire output space like to avoid dimensional collapse, to avoid both dimensional and total collapse. And the way that we did this is we compared with simpler in this scenario. So what you see in this table is basically we take the projector outputs, we calculate the covariance matrix for the projector outputs, and then we look at the eigenvalues of that covariance matrix. So if you look at these eigenvalues are in a log scale. So like as you go down, the values of the eigenvalue very quickly approach zero. So if you look at the graph for simpler, you can see that it uses around like 30 maybe of the around 30 of the eigenvalues are somewhat around 10 to the minus 2. And as you go lower, it very quickly approaches zero, and after like 10 to the minus 5 and even lower. However, when you look at CorInfoMax, you can see that the eigenvalues are all, we get this flat line, which basically tells us that all of the eigenvalues are around the range of 10 to the minus 2 to 10 to the minus 3, and that they are not close to zero. So this tells us that essentially we are making use of the entire output space, and there is no dimensional collapse or something of that sort, unlike what we see in simpler in this case. So this was very useful for us to see that the effect of CorInfoMax on the output covariance representation.
Sure, Shadi, I might have missed some parts of it, but like if you don't use all the eigenvalues, only use subset of it, like if you, this is ordered list of eigenvalues, I guess, right? Is it?
That's right, yes.
So if you just like use subset of it, how much accuracy do you get? Like, do you, like if you like, if I take the yellow one and use the eigenvalues up to 20, so like, do I get a highly accurate result as well, or like, or not?
So in this case, we are not like using certain eigenvalues. Like this is just, we are getting the projector outputs, and basically like we are using them for like a linear classifier. We don't do any sort of like dimensionality reduction based on
right.
Well, we just basically want to see whether the outputs of the projector are like basically have some dimensional collapse problem where they are not using or not utilizing the full output space. But we have not tried like an experiment basically on like dimensionality reduction or something of the output space. That would be an interesting experiment to test.
Okay. Yeah, I was just wondering if dimensionality reduction will give you still reasonable results. Like I'm looking at the graphs and up to 20, 25 seems like you may get a good results, but yeah, it's worth to test it out, I guess.
I agree. Yes, thank you. So another thing that we also wanted to visualize is how the like representations of different classes are clustered. And the way we did that is basically we trained on CIFAR 10 for 1,000 epochs, and then we looked at the test set and visualized it using t-SNE to project it to three-dimensional space. And here you can see the different classes in different colors. And as you can see, the model does, like the outputs of the model are clustered. So you can see like different classes and different clusters in different parts of the 3D space. And this basically shows us that like it is doing some sort of clustering in this output space for these different classes. So to conclude, what we presented today is our algorithm CorInfoMax, which is a novel self-supervised learning framework. It is based on maximization of correlative information, and it manages to avoid both total collapse and dimensional collapse, as we have seen in the eigenvalue experiments of the covariance matrix. It also shows competitive or state-of-the-art performance in many tasks that we have evaluated on, and it also has reasonable computation complexity. Of course, this is not like the end of our experiments. There are many future possible research directions. So one thing that we want to look at is whether we can develop a more systematic hyperparameter selection method for the loss function. Maybe we can come up with like a more mathematical way of selecting the different hyperparameters for the loss function specifically. Another thing that could be interesting is to look at the effectiveness of CorInfoMax in maybe different modalities or in multimodal scenarios. And of course, we also would like to test out different encoder architectures and whether that makes a difference at all, if at all, in performance. And of course, there are many other possibilities, just we could not list them all. So this brings us to the end of the talk. Thank you all for coming. We share all our code and all our materials on the GitHub repository, and you can access that by using the QR code. And if you have any questions, please let us know. We would love to answer your questions.
Can I ask you a question?
Sure,
thanks for the presentation and congrats again for the Neurops paper. So I think you train your twin architecture with augmented samples, right? In the sense that you apply some augmentations and then expect them to give correlated results. But I don't remember that you mentioned about how you do this augmentation. Is it something standard you do, or?
Yes, I'm sharing.
Okay.
Maybe
I missed it. There was a slide for them.
Yeah, so that you can share.
Okay, thank you. Sorry. Okay. For this augmentation part is actually it's in the supplementary part, not making so crowded about presentation. Actually, it's a little bit standardized in the self-supervised learning task. So, for example, these parameters and these transformations are used also in bio and BICREC method. It's same as these methods. We do not change the parameters for that. We use exactly same transformations and the randomized parameters. This is parameters for randomized. So in each iteration, select with these different range of augmentations as using random resize cropping and or color jittering or grayscaling is that. But what we have seen during that period of time, we have seen also the other methods, parameters for augmentation 1 and augmentation 2. These transformations are standard, but sometimes these augmentation parameters are changed. We have seen these augmentation parameters, how make this difference. For example, Gaussian-Euler probability and solarization probability change with the augmentation 1 and augmentation 2. This makes some improvement our performance, being a little bit aggressive on this difference, make some improvement. It was the interesting result which we have seen.
Okay. Also, we don't really see geometrical transformations here, mostly transformations on pixel values, right? Except maybe flipping. There's no rotation, no translation type of.
Yes, there's no just horizontal flipping with.
Is there a specific reason for that? I mean,
can I add a comment? Serdar Shadi, correct me if I'm wrong, but basically when we first started doing this, we weren't paying too much attention to augmentation and using the standard augmentation that comes with, you know, whatever package we're using. But it turns out that augmentation, the success of the approach is very sensitive to augmentation.
Mm-hmm.
And once we realized that, we basically started using the augmentation formulas that we copied from the previous best papers. Unfortunately, we didn't do extensive ablation studies on this. We did some. I think Shadi did some grid search with the augmentation parameters. But what we found that you know, changing the augmentation really affects the performance a lot, which is, I guess, in some sense expected, because what you're doing is you're changing the image in two different ways, and you're saying, you know, these images still should be considered the same. So this means whatever task you have in mind, the changes you apply should not change the categorization of the image. So for example, if there's a cat in the image and when you crop it or flip it, it's still a cat, right? So in that sense, it's expected that the type of augmentation matters. And we found that empirically as well, that it's very sensitive to what augmentation parameters you use.
Okay, so we don't know what would happen if you had rotations and the geometrical transformations applied on this. So this is
Shadi, when you were experimenting, did you try any of those types of augmentations that are not on this list?
I don't think so. So rotations and geometric manipulations, no, we did not do that.
Because, you know, so the premise is that when you apply these transformation on an image, and when you use this twin architecture, I mean, this architecture that you trained using this twin architecture training, whatever, then you expect that the latent representation that you get somehow remains correlated, right? And this latent representation possibly models some factors of variation. And these factors of variation along some dimensions, probably, right? And those factors of variation correspond to the probably the augmentations that you apply. So one dimension is, I don't know, for rotation, I'm just exaggerating, but the other dimension is flipping, whatever. Maybe if it's a face, it's a facial expression that you're capturing in those dimensions along latent representation. So the remaining dimensions remain actually correlated. I mean, unchanged, so remain correlated. So only the dimensions are expected to change along those factors of variation, which are affected by this transformations that you apply, I guess. So, so that is also maybe the transformations that you apply, for instance, rotations and other types of things also are expected to work on this. Probably if you apply these things, and maybe that even can make your representations better in that respect.
So one thing that we have tried, other than like just these transformations, is using like some random augmentation approaches, where they basically like sample random augmentations, which do include rotation. But that's like a somewhat different than just simply like a percentage chance of doing a specific augmentation. Unfortunately, for these other like randomized transformations, we did not see an improvement in performance. And as Deniz Hoca mentioned, like most applying different augmentations to every branch with these like extreme changes in the in certain parameters was what showed us the best performance. We did not find that for using like these randomized augmentations approaches, but of course, like we did not do a very extensive search on that.
Okay, thank you.
I have a question. Alpercan, how did you come up with the idea? Did you have like some hunch about pushing away the X's, and then you had LDMI at hand, and then was it like Big Bang as a result of it, or did you start from that point?
Actually, this determinant maximization is used in unsupervised learning for matrix factorizations. So in that, the idea is the latent factors are spread so that you use that information in the degenerative model, exploit that information to find your factors in the matrix factorization. So we were thinking that we looked at actually contrastive methods and see that they use the negative samples to do that expansion space, but we have seen that the determinant maximization can achieve that. So initially we didn't look at that from the information theoretic perspective. So we just looked at basically just for spreading the samples. Then in parallel, I was working on the blind source separation problem, and it was successfully doing this source separation for basically linear inverse model. And then I was thinking what the stochastic interpretation for that can be, and then I basically come up with the idea that we can look at this as a LDMI maximization principle. But that was not directly translated into this because we were like minimizing the distance between. So it was not arbitrary linear mapping. We were just minimizing. So we had to transform the CorInfoMax objective into that form by doing that linearization on the local determinants.
So basically, you knew what you wanted in the end. You went.
That's right. Sort of. So we did actually our initial experiments without the information maximization principle, just in order to remove the negative samples. We replaced negative sample effect with the determinant maximization, and then we basically fit to this cost function. We basically approach this cost function from the LDMI cost function, so we rederived it later.
I guess the biggest challenge, what was it like? Maybe more for more Serdar and Shadi, like when you were implementing, was it like computationally? Did it work in the first computing the determinant and taking the log? And was it like?
I guess Serdar and Shadi can comment better, but I mean, since the determinant is not really used in the typical setting, so we had to we have some the covariance computation requires that you got a limited batch size. So from that batch size, if you just compute the correlation of that batch size, that's not adequate. So you need to run like a basically autoregressive estimator for the covariance, which uses the previous batch values. So when you do that, it took some time to define like gradient free variables and so on to make sure that we are not doing wrong things. But once we handled that, that basically, then it worked smoothly, I guess. But you need to adjust this epsilon parameter and so on. That is sort of like a hyperparameter search type of thing.
Was this the most challenging part, or was it more challenging to convince the student? We had so many experiments.
I don't know. I mean, what do you think, Serdar? Did we have any? I guess, I mean, fine-tuning we did obtain good results at the early times, but it was not like very close to state of the art. Then basically hyperparameter tuning and so on, we were able to increase the performance thanks to the hard work of Shadi and Serdar. Yes, but I mean, initially idea, I guess, worked. I don't know, Serdar, you can comment on this, I guess.
Yes, similar idea, similar experience about this issue. So actually coming through the one point is easy, but for the getting the state of the art is some small changes sometimes in the architecture or something like that. That makes the difficult part, I think.
Yeah, I give this as an example to my students of perseverance. So no matter how good the idea is, and Alper Hoca's idea was really good, if we worked on this for 12 months, the first 11 months, we were actually under the state of the art. So it wasn't publishable. But we didn't give up. Well, Serdar and Shadi didn't give up. And they pushed it and they optimized it. So don't give up on your idea early. If at first it doesn't seem to work.
There's a question on the chat. Oh, you answered it, the first one, the second one.
Yes.
You can read the question to Shadi.
Okay, so the question is if we have done any ablation studies with the projected layers for downstream tasks. As far as I know, Serdar, correct me if I'm wrong, in all of our settings, we were just getting rid of the projector. I don't recall any experiments where we tried keeping the projector for downstream tasks.
Yes, in that way, but yes, in all the experiments are we are throwing the projector after pre-training, but projector for projector, sorry, I misunderstood the question. Projector layers for downstream test. Actually, we didn't try, but according to this, because the projector layers, actually, this is in some sort of sense why we use projector layers, actually, because we do not want to specialize in the main task, the first pre-training task, because we don't want this and take away from that specialized part in some sense. And we have more generalized version of the encoder part, and we are using that part in encoder in downstream task is my insight in.
But is the question asking about the ablation study on the number of projector layers, or?
But as I understood at the beginning, I have understood that, but as I understood, the question is, are you kept the projector layers for the downstream tasks?
Because you did some basic experiments with different number of layers for the projectors, I guess, right?
Yes, but the question is projector layers for downstream tasks. So actually in downstream task, we do not have projector layer. So okay, yes. And so yeah, yes.
Yeah, but it's definitely worth exploring. I mean, looking at different parts of the projector, we did not do that in the experiments for this paper. Especially not keeping the whole projector, because typically the last dimension is pretty small, like 128 or something. It might not be suitable for like ImageNet classification, for example. But yeah, we'll leave that to future work for now.
One last question. Would it be possible to do this without Google Cloud credits?
Because it had an impact on the ImageNet 1K experiments a lot, especially during the rebuttal period.
1 week of no, you have 2 weeks or
2 weeks. Actually, it was like 1 week for the response, I guess, 1 week for discussion of something. So you could still do some experiments during the second week, I guess.
I'll update it.
But we are finished, I guess, with the first week.
Yeah.
okay, resources are very important.
Yeah.
Thank you. Congrats again.
Thanks, everyone.
Thanks so much.
Thanks.